This is part 1 of the trigonometry section of our aeronautical engineering course. Trigonometry is the study of triangles. A triangle may have 3 acute angles like that, that's not really acute, that, and let's call it that. Each of these angles, that one, and that one, are all less than 90 degrees. 90-degree angle is 1/4 of a circle. Like for instance, if you have a compass and there's north and there's south, there's east and there's west, and some compasses have the numbers here. They'll have a 0 for north, a 90 for east, a 180 for south, and a 270 for west. 90 degrees between north and east, 90 degrees between east and south, 90 degrees between south and west, and 90 between west and north. Okay, a triangle may have a right angle, or a 90-degree angle, and 2 acute angles. Like for instance, here's a right angle. See how this is 90 degrees, and the other angles are going to be acute angles right there. Okay, there could be a little long, skinny one. Ooh, better make that the right angle on this one. These are the acute angles. That one may not look all that acute there, but it is. It's almost 90 because this one's almost 0. And here's the famous 45-degree right triangle. That's a right angle, and each of these is 45. Okay, a triangle may have an obtuse angle, like, there we go. That's an obtuse angle. It's greater than 90 degrees. Of course, that leaves these both being acute. Acute means sharp. Obtuse means dull. Okay, some famous right triangles are the 30-60. Let's see if we can draw one of them. Ooh, should have gotten a better eraser for this, huh? Okay, here's a 30-60. Okay, one angle is 60 and the other one is 30, and then it's a right triangle. Let's call that 30. 30 degrees, 60 degrees. That's a 30-60 right triangle. Okay. Another famous triangle is the 3, 4, 5 right triangle. That's a right angle. That can be 3 inches, that can be 4 inches, and if they are, then that's 5 inches. If that's 3 miles and that's 4 miles, that's 5 miles. Okay. Then there's the 5, 12, 13 right triangle. Okay. We can use Pythagoras' theorem to figure out the lengths of the legs and hypotenuse of a right triangle. Pythagoras says a squared plus b squared equals c squared. Okay, a is the length of one leg, like we could call this one A. The other leg would be B, and the hypotenuse is always C. Doesn't matter which of the legs are A and B. Okay, we'll call that one A, that one's B, this one's C. Okay, there's a leg, that's A. There's another leg, call it B, and the hypotenuse is C. The hypotenuse is always longer than any of the legs. Okay. Okay, if we have a 45-degree right triangle, let's go ahead and I'll draw one of them up here. There's our right angle. Okay, right there. This is 45 degrees there. Okay, if we have a 45-degree right triangle with one of the legs equal to an inch, this would be 1 inch from there to there. Okay. How long is the other leg? Here's the other leg, and how long is the hypotenuse? Okay, let's first figure out how big the other angle is. The angles of a triangle always add up to 180 degrees, regardless of how the triangle is shaped. A right triangle, by definition, is a triangle with a 90-degree angle. If one of the acute angles is 45 degrees, the other acute angle must also be 45 degrees. So there's a 90, there's a 45, and they all have to add up to 180. So 180 minus 90 minus 45 equals 45. So this has to be a 45-degree angle right there. Okay, we can prove that the angles of any triangle add up to 180. Give me a second to erase all this. Make us a little room here. Oh boy. Okay, let's say we have a triangle, any old triangle, doesn't matter what. Okay, and let's say we draw a line through one of the vertices. In other words, you have a vertex, and a vertex, and three vertex, or a vertex plus a vertex plus a vertex equals three vertices. That's plural of vertex. Okay, we've drawn a line through one of the vertices. Okay. Okay, and we've drawn it parallel with this opposite side. So anytime a line intersects two parallel lines, these angles, let's see, tell you what, let me draw this a little different. Okay, let's say this is our triangle. Okay. There's our parallel line, parallel with that line. Okay. This angle and this angle, or what you call alternate interior angles, they're equal to each other. Okay, this angle and this angle are also equal to each other. They're called corresponding angles. And of course, this angle is equal to itself. So what does this angle plus this angle plus this angle add up to? Well, this angle is equal to this angle. This angle is equal to this angle. So this one, and this one add up to this one, and this one, which is 180. Right there. That shows us how the angles of any given triangle always add up to 180 degrees. Okay, no matter which triangle we look at, it works. Okay, so let's get back to our 45-degree right triangle. Both acute angles are 45-degree angles. There's our 90. Both acute angles are 45. Okay, have you ever heard of a guy named SOHCAHTOA? Okay, his name can be used to find the lengths of the sides and hypotenuse of our triangle. The sine of 45 degrees is equal to the length of the opposite side. See, here's our 45-degree angle. Well, this would be the opposite side is opposite of that angle. this side would be opposite of that 45-degree angle. Okay, the sine of 45 degrees would be equal to the length of the opposite side divided by the length of the hypotenuse. Let's call this A, call this B, and this C. So the sine of 45 degrees equals B over C. And the sine of this 45-degree angle equals A over C. And obviously B equals A, because A over C equals B over C. And with a 45-degree right triangle, the legs are always equal to each other. Instead of saying A squared plus B squared equals C squared, let me go ahead and erase this. Okay, Pythagoras' theorem, A squared plus B squared equals C squared. In the case of our 45-degree right triangle, we determined that A is equal to B, so A squared equals B squared. So we could just say A squared plus A squared equals C squared if we're talking about a 45-degree right triangle. Or we could say B squared plus B squared equals C squared. Okay, so if A squared plus A squared equals C squared, that means 2A squared equals C squared. Okay, let's say we take the square root of each side of this equation. Anytime you have something equal to something else, as long as you treat each side equally, they'll stay equal to each other. You can add something to one side, add the same to the other, they're equal, divide one side, divide the other, take the square root of one side, take the square root of the other. That's what we're going to do. So we'll just draw our square root sign over each of these, and we have the square root of 2 times A equals square root of C squared, which is C. Okay, the square root of the number is the number that multiplies times itself to equal that number. For instance, square root of 25 equals 5, because 5 times 5 is 25. Square root of 16 equals 4, because 4 times 4 is 16. Want to guess what square root of 9 is? You got it, 3, because 3 times 3 is 9. Okay, the square root of 2 doesn't work out quite as pretty as the square roots of 9, 16, and 25. It's an irrational number. If you want to see what it is, touch 2 on your calculator and then touch the square root sign. Let's see here. Let's clear it. 2. Well, the square root sign's above this button, so I'll hit my invert to get my square root. It says 1.414213,562. We'll just call it 1.414. That's what the square root of 2 is. I didn't draw that too good, did I? Okay. We can use this information to figure the length of the hypotenuse of our 45-degree right triangle. Remember what we determined a while ago, that the square root of 2 times A, let's see, yeah, square root of 2 times A equals C. Okay, whoa. Uh-oh, I jumped ahead of myself here. Okay, square root of 2 times A equals C for a 45-degree right triangle. Ooh, we're running out of time. We'll take up where we left off in part 2.